Visualization of the key air properties influencing derived functions. Abstract. The main objective of this paper is to suggest the best correlation between the temperature and temperature-dependent air properties. The main air properties presented in this paper are specific heat, density, dynamic viscosity, kinematic viscosity, thermal conductivity, and thermal diffusivity. The reliance of these air properties with temperature is studied at atmospheric pressure. At the end, details of a MATLAB computer program are presented. This computer code would be useful for the students in further detailed studies and hand calculations. Keywords: temperature, air properties, specific heat, density, viscosity, thermal conductivity, diffusivity. Nomenclature. Cp equals specific heat in kJ/kgK. T equals temperature in K. Equals density in kg/m3. Equals dynamic viscosity in Ns/m2. K equals thermal conductivity in W/mk. Equals kinematic viscosity in m2/s. A equals thermal diffusivity in m2/s. Introduction. This section provides a brief survey about the relevant literature and preliminary considerations of various thermodynamic properties of air. The first author, Donald W. Mueller, Jr., Hosni I. Abu Malaa, presented a study on isentropic compression of a gas with temperature-dependent specie.c heat capacities 1. The values of coefficients to solve thermodynamic properties are taken from this paper. The work by Sanford Gordon, Bonnie J. McBride III has also given the polynomial equation to solve specific heat, enthalpy, and entropy which are dependent on temperature values. Density relation with respect to temperature is given by F. J. McQuillan, J. R. Cullum, M. M. Jovanovic in their paper 11. The most satisfactory law of variation of viscosity of a gas with temperature was proposed by W. Sutherland 7. R. Byron Bird, Warren E. Stewart, Edwin N. Lightfoot, in their paper 12 have considered an example of molecular momentum transport theory and introduced Newton's law of viscosity along with the definition of kinematic viscosity. Canon John Rozier in his paper 13 had introduced the term heat diffusion, which describes the heat distribution in a given region, which may be further used with Fourier's law to determine the heat flux. A reliable experimental equation for thermal conductivity covering a wide range of temperature is presented by K. Kodaya, N. Matsunaga, and Inagas 6. 2 governing equations: theory, experiment, empirical. A specific heat. The polynomial governing equation for specific heat as a function of temperature 1 is presented as Cp equals R, a 1T2 plus a 2T1 plus a 3 plus a 4T plus a 5T2 plus a 6T3 plus a 7T4. The coefficients value are given with the attached MATLAB program. B. Density. Density of air can be found using the relation equals P/RT, which requires the values of pressure, gas constant along with the temperature. In the relation given below, at atmospheric pressure, density can be found with the help of only temperature. This inverse relationship is given in the paper 11. Equals 351.99/T plus 344.84/T2. See dynamic viscosity. The simple expression for a theoretical model is given below for the dynamic viscosity of a gas. /0 equals T/T0, 0.5, 1 plus C/T0, /1 plus C/T. Where 0, T0 and C denote the reference values of the dynamic viscosity, absolute temperature, and the Sutherland's constant respectively. Using Holman's values of /0 based on experimental measurements 8, the value of C was calculated to be 113. Based on experimental data from Barus 9, the above equation holds good for a temperature range of 273 K to 1200 K. Since experimental data is required to specify 0, the Sutherland's theoretical expression takes a semi-empirical form as shown below. Equals A, T 1.5 / C plus T. Where A equals 1.47 * 10 to 6 kg / MSK 0.5, calculated using 0 at T0. The above equation is further modified by using a multiplication factor, as suggested by James J. Gottlieb, David V. Ritzel 10, such that dynamic viscosity could be calculated for the temperature range of 78 K to 2500 K. Equals A, T 1.5 / C plus T, 1 plus 1.53 * 10-4, T/C minus 1, 2. D. Kinematic viscosity. Referring to Bird et al. 12, based on the analogy of Newton's viscosity equation with heat and mass transport, kinematic viscosity, often called as momentum diffusivity, is given by == E thermal conductivity. The keystone of conduction heat transfer is Fourier's law, which defines a crucial material/transport property, viz. thermal conductivity. This property depends on the atomic and molecular structure of matter. The trend in thermal conductivity among the different types of matter is K solid, liquid, K gas. In gases, the molecular collisions increase with rise in temperature, which indicates K increasing with temperature. For gases, variation of K with temperature can be presented both theoretically and experimentally. Theoretical, thermal conductivity of gases depicting the effect of temperature, pressure, and chemical species may be explained in terms of kinetic theory of gases 5. K equals CV.mfp, where v is mean molecular speed and .mfp, the mean free path, which denotes the average distance traveled by a molecule prior to a collision given by .mfp equals kBT/1.414 pd2p, where kb is Boltzmann's constant, d is the diameter of the gas molecule, and p is the pressure. Experimental, the uncertainty over thermal conductivity of air is large compared to other thermal properties. This is quite evident from the trace of extensive amounts of experiments carried out during the mid-19th century. In fact, the precariousness in experimental determination is larger than the theoretical way of arriving at a value of K as a function of temperature due to the difficulty exhibited in measuring it. In order to cover a wider temperature range and reliability of results, the below equation derived from the extensive study done by K. Kodaya, N. Matsunaga, and Nagashima 6 is used. F. Thermal diffusivity. In heat transfer, the ability of any material to conduct thermal energy relative to its ability to store it is measured as thermal diffusivity. In the one-dimensional heat equation derivation by Canon 13 from Fourier's law and conservation of energy, it is seen that the thermal diffusivity is given by A equals K/Cp. 3. Sensitivity analysis. A graphical representation. The graphs showing the variation of air properties with respect to the temperatures are shown below, and a comparison with the values available from the Heat and Mass Transfer Data Handbook by C.P. Kothandaraman and S. Subramanian is done for the validation of all the correlations presented on this paper. The trend of errors is also plotted in the graphs to clearly understand the range of temperatures over which the correlations are reliable. 4 observations. The comparative studies shown above have red curve corresponding to the values obtained from Heat Transfer Data Handbook, the blue curve corresponds to the values obtained from correlation suggested in the paper, and the black curve shows the trend of error with respect to change in temperature values. From figure 1 it is observed that the errors are within plus or minus 0.2% for the temperature range of 273 K to 1100 K and go higher up to 1.2% beyond elevated temperatures of 1100 K. Similarly, for other properties the error limits are summarized in the table 2 below. It is clear that the difference between values of air properties obtained using the correlations and the data handbook is negligible, since the error, as shown above, is less than 5% in any case. The maximum error of about 4% is observed in the case of thermal conductivity and thermal diffusivity within a range of 650 K to 750 K only. V. Concluding remarks. We have presented the correlations for specific heat, density, dynamic viscosity, kinematic viscosity, thermal conductivity and thermal diffusivity varying with temperature over the range of 273-1300 K. Graphs have been plotted showing the variation of these air properties. With respect to temperature, for validation of results the curves have been compared with the values given in Heat and Mass Transfer Data Handbook by C.P. Kothandaraman and S. Subramanian. The correlations suggested in this paper are found satisfactory when compared with the Data Handbook air properties. Finally, a MATLAB code for students is given to strengthen their understanding of these thermodynamic properties. Further study is needed to accommodate the impact of varying the pressure and chemical composition of air on the correlations presented. Acknowledgement. Authors of this paper would want to record their indebtedness to Department of Mechanical Engineering, MVJ College of Engineering Bangalore, Continental India, and GKN Aerospace India for providing the facilities to carry out this research.